Very good morning and greetings, friends and my dear students. Today I am going to take the video lecture on the moment area method of deflection. Also, it is called as Morse deflection method of finding the solution of slope and deflection. Before going into the moment area method of deflection or Morse method of deflection, all of you know that when a load is applied on a beam, definitely there will be a slope and a deflection at the required point in the case of a span of a beam. The method of deflection can be determined by various methods like double integration method, Maclaurin's method, moment area method, conjugate beam method, and strain energy method. Here we are going to see about the moment area method of deflection or Morse method of deflection. So here I am going to use the notation EI, that is the flexural rigidity of the beam material, where E is the Young's modulus of the material, I is the moment of inertia about the neutral axis of the beam, and capital A is equal to area of the bending moment diagram between the given points A and B in the case of a beam. And AX bar is nothing but the first moment of area of the bending moment diagram where the slope and deflection is required between the beams. So here there are two theorems are used. The first one is Morse theorem 1 or moment area theorem 1. This theorem states that the slope of a given beam at any required point is defined as the area of the bending moment diagram between the sections A and B divided by the flexural rigidity of the beam. I can put in terms of equation theta is equal to capital A divided by capital EI. So in this way you can find the slope of a beam at any given point. It is measured in terms of radians. If we want to convert in terms of the degree, we can multiply the corresponding theta value into 190 divided by pi. You will get in terms of degrees. Similarly, the second theorem of moment of area or the Morse theorem 2 is to find the deflection delta or y. We can call it as the notation for the deflection. So the deflection at any given point of the beam is defined as the ratio of the first moment of area between the two required points A and B divided by the EI, that is the flexural rigidity of the beam, into X bar value. Or we can give in terms of the equations delta or y is equal to AX bar divided by EI. Already I have told you AX bar is the first moment of area of the free bending moment diagram about the required points A and B. And EI is the flexural rigidity of the beam. It is given in terms of kilonewton to meter square or Newton into millimeter square. For whatever be the deflection is required in a given beam. For example, in the case of a simply supported beam with two ends having hinged support and the roller support, the slope at the support ends is given as capital A by EI, that is equal to WL square by 16 EI. If you are solving the equation, you will get. Then in the case of the deflection of a simply supported beam with a central point load, W, will get the deflection at the midspan, that is equal to delta max or Y max, that is equal to W into L cube divided by 48 EI, where W is the applied load at the center point and L is the span of the beam in meter or millimeter, and EI is the product of the Young's modulus and the moment of inertia about the neutral axis. This product, which is called as the fluxural rigidity of the beam, and already I've told you the unit is kilonewton into meter square or Newton into millimeter square. So this is the way you can able to find the deflection of a simply supported beam with a central point load. Similarly, in the case of simply supported beam with the UDL, so W per meter run over the entire span of the beam, the theta value can be measured by using the Morse theorem method or moment area method. 1 is equal to WL3 by 24 EI, where EI is the fluxural rigidity of the beam in kilonewton meter square, and the deflection will be occur at the midspan, and it will be maximum at the midspan only because it is a symmetrically loaded beam. So delta max or Y max is equal to 5 into WL power 4 divided by 384 EI. WL power 5 into WL power 4 by 384 EI, where small w is the intensity of the UDL in Newton per meter or Newton per millimeter, and E is the fluxural rigidity of the beam, L is the span of the beam. So like that you can apply what are the type of beams, and the loading is a symmetrical loading or a simply loading. Can apply the moment area method to find the slope and deflection in this moment area method or Morse theorem method. So this is about the moment area method and the definition of Morse theorem 1 and Morse theorem 2, which is called as the moment area method 1 and moment area method 2. So then we can able to solve the problem by using these two equations, the case of moment area method 1 and 2 theorems. So thank you very much for patient listening for today's video lecture on the strength of materials, which is about the dealing of the deflection and slope using the moment area method or Morse theorem method. In the next class, we can see some numerical problem based on the practical applications. That is most important. What would be the theorem and other analytical method is there? We have to solve by using the practical application of the problem. So then only you can easily understand the problem and able to solve the problem. Thank you very much for patient listening. Thank you. வாழ்க வையகம், வாழ்க வளமுடன்.